Hi everyone, this is a video on rotational dynamics. So in this problem what I'm going to do is actually use the definition of torque. That torque is now moment of inertia times angular acceleration. And I'm actually going to combine it with our previous topic of forces, F equals ma, and show you how you can use both of these as a way to solve problems. So here is a typical question, if you will. And this is, I think, a really good example to show this transition between the two types of definitions of force, whether it's linear force or rotational force. So here is a question. So you have a student that's holding a string with this thread, and kind of like a yo-yo if you think about it, right? And it's holding it above the floor at some height h. This thing has a mass of m, a radius of this. And then it gave us the moment of inertia. Now, moment of inertia, I remember, is how an object rotates based on its mass. So it's kind of like rotational mass. This is what I is. And for all problems with rotation, where the mass is absolutely changes the type, how the object moves. So what we do is we have for every single shape, roughly, we have what is called moment of inertia. How is the mass distributed? And then this models how the shape will rotate. So that's rotational inertia, or I right here. Now, if they don't give you the I in the problem, you have to look it up, but they gave it to us because they said the solid cylinder has a moment of inertia of I equals 1/2 mr squared. So that's this value right here. Now, this problem has specific requirements. It says m, r, and h, and fundamental constants. So that basically means you can use things like g and pi. So if we have things like time or final velocity, it's not, you might have solved it right, but it doesn't want that in the question. So let's go ahead and take a look at what's going on. It wants the linear acceleration as it falls. So it wants basically a. So even though I kind of know where this problem's going, let's just be dramatic here and take the easiest route, right? I always recommend that looking at this the easiest way first before we go complicated. So I see that we have an H. This thing's initially at rest, I believe, so the student holds it wrapped around as shown above, then it drops it. So we're actually starting at rest here, technically, right? We have some height of H right here, and this thing is going to accelerate. So I immediately thought, okay, H is going to be 1/2 at squared like this, because if you look, this is the equation, by the way. So this is our kinematic equation, VIT plus 1/2 at squared. And if the initial velocity is 0, then this whole thing is just 1/2 at squared. Now I used h because that's what they want us to use here. But the problem with this is time, right? Time is not a variable that we can use in this problem. So although this would be the easiest way, we kind of have to scratch this idea. So I just want to show you that you can't use this one for that reason. So then it comes down to, all right, what can I use? So if you notice here, I can think about this as a torque, right? So if you notice that this thread right here, I'm going to call this T for tension. And this is R right here. So notice that the tension is applied at the edge of the circle right here, which means, by definition, that's our torque. So we have a torque on this as TR, like that. But as you can see right now, this is still not helpful because we need A. So what we know about T is actually we can relate it to torque over here. So I'm just going to move over here. So I could say I alpha is equal to TR. And I could say, oh, I remember how I can relate alpha and R. So remember, linear acceleration is R alpha, like that. And I can get I in terms of the variables we know. So I'm going to plug that in. So I'm going to do 1/2 mr squared. That's all I times R alpha. I'm sorry, I want to substitute alpha for A. So if I do that, that would be A over R. A over R, that's for alpha, equals T R. Cool. So far so good in that we have now alpha as part of our problem. So I'm going to go ahead and just simplify a couple things here just to make things a little easier. So I see that this is below, so that'll cancel out one of these r's just like that. So I get 1/2 m r alpha equals T R. Now the problem is, I mean, we can simplify one more. We can see that the r's do go away. So I get 1/2 ma equals T. Now we would almost be there, but again, this is not one of the acceptable variables that we can solve with here. So you can see that we have a problem with T. But we're almost there. This is almost where we need to go, where that's alpha. So I need to figure out T. So this is when I'm going to use linear forces, or in other words, we're going to use the fact that we can treat this like Newton's second law. So I'm just going to redraw it right here. So you have two forces acting on this. We have a tension acting up, and then the weight of the object acting down. Actually, I may just write this as capital M, because we do know the mass is modeled as capital M. So that's the free body diagram of this situation. Now when it comes to Newton's second law, it doesn't matter where the forces are, but we do have to model what's going on. So if we were thinking about this, this thing is actually falling down, right? So the acceleration is directed down like this. So I'm going to call that the positive direction, if you recall how we set these up, right? So if that's positive, mg is going to be positive minus the tension, because the tension is going to hinder this object from falling, because without the tension this would just free fall. So this is acting as a resistive force, so that's why I'm modeling as a negative sign, because it acts as a resistive force. And this whole thing will accelerate through ma. So notice I could use the linear sense to solve for t, and then I'm going to plug it into here. So let's go ahead and do that. The way I'm going to do that is I'm going to subtract ma from this side and add t from that side. So let's go ahead and do that. So I get mg minus ma, because I'm subtracting this on this side and bringing t over, because that just gets me t in one step here. So that's my t. So I'm going to now take my definition of t and plug it into here. So let's write it out. So I get 1/2 ma equals t. So t is this whole thing, mg minus ma, like this. Now I need to, so notice I eliminated t by taking it here and swapping it out, right? Plugging it into here. So we're able to eliminate t, or tension. So that was the technique here, using the linear force, or Newton's second law. This is Newton's second law application into this. So with that said, I'm going to go ahead and simplify now and figure out what a is. So I have a factor of a over here, so I'm just going to move this over so the a's are on the same side. So what I have is 1/2 ma. Since this is subtracted, I have to add it over. Ma equals mg. Alright, so if you notice, we have m's in every term, and because of that we could get rid of them. So now I have 1/2 a plus a equals g. Just being careful here. So 1/2 plus, essentially this is the same as 1, right? So I'm going to put 2 over 2 for 1 here, so I can add them up. So that gives me 3 halves a equals to g, but I'm solving for a, not g, so I'm going to go ahead and move this over. So the acceleration of this is going to be 2/3 g. And that is the final and correct answer. So let's think about that. Hopefully that makes sense, because if you think about the scenario, right, if this thing has this tension kind of holding it back, without tension, this thing would just fall with a value of g. And notice that the acceleration is less than g, which hopefully I mean, that makes sense because we have this kind of slowing it down. If we got something larger than g, then there must be an outside force pushing it down, which of course is not the case. This would be if I threw it down. But the fact that this is less than g is good. Just like that. So that's part one, finding the acceleration. So the biggest trick here is understanding that when you have this relationship, remember we can use two definitions of torque, right? So we have the first definition of torque, which is force times distance times sine of the angle. Now, I hope you notice that I even just skipped the sine part because this was at a right angle, so that dropped out. But torque can also be related like linear force in terms of the mass and the acceleration of the system. But this, of course, is linear acceleration. I'm sorry, angular acceleration. And then these are equal, so you can set them equal to each other. So this is a tactic for solving these types of problems like this. So you can set them equal like this. It's not always helpful to do this, but if you have a problem, anytime you see something like a pulley system or Atwood's machine, I definitely use this kind of relationship to help me solve the problem out. Okay, that's part one of this whole problem right here. Let's go to part B. Okay, wants the angular velocity just as it hits the floor. So, just going to redraw it just so we have a visual of the system. There is actually a few different ways to solve this. I'll show you, well, why not? I'll show you both ways, right? Just so we can have it in our toolbox of ways to solve things. So same thing, we need H, M, and R. Those are our only ones that we could have the answers in, which of course restricts us to what we can do. So I'm going to show you the first way. The first way is the way that we currently know because we studied this is through kinematics. So the second way I can solve this is through energy. Assuming no mistakes, both of these will yield the same answer. So just because I show you one way doesn't mean it's the only way. So just know that you have some creative freedom in how you want to solve these problems. Oh yeah, so there's this H part. Alright, a very important feature is we do know that this thing is at rest when it starts. Both linear and rotational. This thing doesn't rotate to begin with. So that's a really good feature right here. The question is essentially what is the angular velocity right before it hits the ground like this. So we do know from the previous problem that A is 2/3 g. So we do actually have that from the previous problem. And of course if you're doing an AP question or problem, always go with whatever answer. Even if your answer is the weird answer, like maybe it's bigger than g, that's fine. As long as you plug it in, you still get full credit. Let's take the kinematic version of this. So, I see this as a height, a final velocity, like this. So, I can actually use this equation. So I like this approach because I have all this information more or less. Of course I don't have the final velocity, but remember that I can always relate a linear velocity to a rotational velocity through this equation. So even though I'm solving it in linear, I can then fix it into our angular like this. And that's exactly what I'm going to do because I have a linear acceleration, I have a linear distance, I have a linear initial velocity. So this is what it's going to look like. My final velocity linear is going to be 0, because that's our linear. Of course, this whole term drops out. Plus 2 times my acceleration, which is 2/3 g, times h. And h is an acceptable unit that we can use here. So let me just rewrite this so it's nicer. So velocity squared is equal to, I'm now just going to simplify this as 4/3 g h like that. Now this is squared, so I'd have to square root it to get the answer. But first, before I do, I'm actually going to transpose this linear velocity into angular. So v is equal to r omega. So I'm going to take this and make this into capital R, which is an acceptable value, and do omega but this whole thing is squared here, equals 4/3 GH. So now I'm going to distribute this squared, so I have R squared omega final squared equals 4/3 GH. And now I'm going to solve for the omega final squared is equal to 4GH over 3R squared, like that. And then omega final is the square root of 4GH over 3R squared. Ta-da! And that is our answer like that. Even though it looks ugly with that square root, you could pop that out if you want. You just leave it like that. But that's the official answer. So the big thing, once again, the theme is that we can go from linear to rotational through these relationships. So just knowing these are incredibly helpful, because that's how we can connect linear motion and rotational motion. Now let me go through the motions of energy. So I know I didn't cover this right away, but regardless of where you are in your learning process, it's still good to see energy. So even if you know, we're way far ahead and this is now on energy, you can see how we can use it. So if you think about the energy of the system, and I'll work in green over here just to be different. So energy's in green. Notice that we have this object at some height. So anytime we're displaced at a height, we start off with our gravitational potential energy up here. In fact, since we're at rest, there's no linear kinetic energy and there's no rotational energy. But at the bottom here, notice that actually this is really good because we have rotational kinetic energy. So kinetic energy rotational. And we're going to have kinetic energy linear at the bottom here. So I could set this up as a conservation of energy, where we start off with just potential energy and we end up with some final kinetic energy. So I'm going to go ahead and write that. So gravitational potential energy initial will be equal to the rotational energy final plus the kinetic energy final. Now, R stands for rotational, L stands for linear. I know this looks really crazy, but this is rotational energy and this is linear energy. So, how does this look with our variables? So, GPE is mgh, so it's going to be capital M, G, and there's our H. Good news is that these are all things we can use. Rotational energy, if we haven't studied yet, looks just like kinetic energy, except instead of M, we use I, because now we're using moment of inertia, and instead of V, we use rotational or angular velocity. So it really isn't too much difference. I'm going to write it in as 1/2 I, and this of course will be our final velocity, which is what we are looking for in the problem, plus 1/2 capital M V final squared. So this is the linear part. So let's go ahead and plug in I, because we're almost done here, but not quite. So I get mgh 1/2. Now remember from the previous slide here that I is 1/2 M R squared, and then we have omega final squared plus 1/2 M V final squared, like that. Okay. Now the problem is we're actually almost done, but our problem is this linear component right here. We don't want V. It's not a requirement, so that we are not a acceptable variable that we can use. So we're going to go back to our handy dandy equation right here, and notice that we can make V into our rotational counterpart by plugging in our omega. So I'm going to go ahead and do that. So that's going to be mgh. Since I have this written here, I'm going to go ahead and simplify this. Notice that becomes 1/4 because we're multiplying. M R squared omega final squared plus 1/2 M. Now V is our omega. Now it's final because that's the one we care about, but this whole thing is squared. So I'm going to plug that in first, so r omega. Now this is capital because this is the way the problem is written with capital R, but this is, I hope you realize that that's still R there. Okay, here we go. mgh is equal to 1/2 r squared omega final squared. Now we're going to go over here and do 1/2 m. Now I'm going to distribute the squareds here, so r squared omega final squared. Okay. Everything's looking okay so far. So notice that these are basically the same terms, but we have different factors over here. So let's go ahead and straighten this up a little bit. So what we have is, let's see, 1/2 plus 1/4. So let me go ahead and think about this. So 1/4, I'm going to make this into a common denominator here. So 1/4 m r squared omega squared plus 1/2 is the same as 2/4, right? I hope that's okay with you. And now, because we have a common denominator, we can add them together. So here we go. 1/4 plus 2/4 is 3/4 m r squared omega final squared. Alright, our m's can cancel out. And remember that we're solving for omega final. So the 4 comes up, the r squared goes down. So I get 4gh. And then the r and the 3 come down. Okay, and remember that we have to square root this to get the final answer, so I'm going to go ahead and do it. Square root of 4gh over 3r squared equals omega final. Well, look at that. How shocking. It looks like it doesn't matter what you use, whether you use kinematics or energy. Ta-da, you get the same answer. So, personally, I don't know which one's easier. I think they're both the same, to be honest. It just depends on your preference and how you solve it. You get full credit whether you use this one or this one. But the point is, notice that we could use either one, and that you could, again, translate between linear and rotational kinematics or motion or energy through these relationships. So if it's not in terms of one, you can transfer it into the other. But either way, this is how you can find the final velocity at the bottom based on just the required or the acceptable variables. So notice h is acceptable, r is acceptable, g is a fundamental constant, and of course these are just factors right here. So if you have any questions, just let me know, but that concludes our video of this spool. Now there's more. If you're looking at the question that I gave to you in class, there actually is more to it. But we're not going to cover that because it's not covered on the AP Physics B, so it's all about rolling without slipping. So basically it just means it's sliding at some point, so you have to include that in your model as you write out your equation. But like I said, we're not going to cover that. If you're interested in it, I'll be happy to go over it with you. But I'm going to end at part B right here. Alright, I hope you enjoyed this video, and I hope you learned a little bit.